All right, thanks for coming to this talk. It seems to be my luck that at conferences I'm often up against people I admire at the same time in the other room, and that is the case here. You should definitely check out James Long's works on Sweet.js macros for JavaScript since you came to this talk and you're missing that. But since you did come to this talk, I think you're in for a treat. I'm going to talk about a project called Regenerator, which is an effort to take one of the really cool, I think the coolest feature of the next version of JavaScript, ECMAScript 6, and simulate it using JavaScript of today. So you can go ahead and use that feature from the future in the present, or in a browser, more to the point. I'm Ben Newman, and I work at Facebook. I released Regenerator with my team at Facebook, which is the JavaScript infrastructure team, and we have been maintaining it actively, so it's not just thrown over the wall. If you want to talk to me specifically in following up on any of this stuff, or just get to know me, I'm Benjamin without the I on most forms of social media, as you can see there. So when we released Regenerator, I wrote up this sort of call to action page and posted it on Hacker News, and got into like the top 5, and the comments were all really surprisingly appreciative. There was very little backlash. And one of the things I think went well about this launch is that it signals, just from a headline like this, that you might need to have or want to have a little bit of context, a little bit of experience with the idea of generator functions before you have an opinion about whether the way we did it was correct or the best way of doing it. And so I live in New York, and one of our local meetups is Brooklyn JS. At the last instance of Brooklyn JS, Brittany Starose gave a talk about technical writing, and she gave me a term that now sort of helps me conceptualize this idea. So you have low context and high context audience members. And you can write in different ways, and you should write in different ways when your audience comes in with some context versus when they come in without much context. And so I'm making a bet that JSConf and the group of people who have come to this talk stand the best chance of having a little bit of context around these issues of anyone, anywhere. So I hope you don't mind if I abuse you with what I would consider to be a pretty technical talk. There's a lot of code, and I just encourage you, if you want to follow along at all, look at the slides. Read along with the code as I'm talking about it. Otherwise, if I'm just talking about it and you haven't been looking, you may find yourself lost, which is totally fine. I'll try to change the tone of my voice when there's something like sort of independently interesting, and maybe you can get back on the path. But with that warning out of the way, so calls to action, right, are something we often feel like issuing when we've built something that we're proud of. We think other people should use it. We think it's a better way of doing things than the way things have been done in the past. And we want to tell ourselves that we and everybody else should have been doing it this way all along. And GitHub is indeed littered with better ways of doing things, really better ways for someone of doing something that never quite caught on. And why is that? Well, I would claim that in addition to having a bright idea about how you ought to have done something from the beginning, you can't just go back and start over from scratch. If you could, it would be easy to do it the right way from scratch. But you also have to have a second clever idea, which is how to get from where you are right now with the application stack that you've inherited to that new place that is as if you started from scratch with all the right ideas. So there has to be a way forward, not just backwards and then forwards again. And I would go further to claim that programming languages are notoriously difficult in this way. They're difficult to fix forward. So if I can ask an inflammatory question that may not be so inflammatory here, because this is a JavaScript and not a Python conference, why is it, it's been since 2008, and Python 3 is definitely a better language in a lot of ways than Python 2. And Python 2 is one of the most successful programming languages in the history of programming languages. Why is it that big projects haven't switched to Python 3? Django, for instance. And so I don't know, how many people have used Python of any version in the room? It's almost everyone, maybe 80, 90%. How many people have written a line of Python 3 that runs in production? All right, we can walk away from this discussion. Okay, so I don't want to go into this too much, but Python 3 is a lot of new features, some of which are fairly trivial to switch over to. They have a 2 to 3 script to convert your print keywords to print functions, since that's a small cosmetic thing that changed. But there are also differences in the semantics of Unicode handling in Python 3 that are definitely the right way to do things. Byte strings in Python 2 are a source of a lot of trouble, but you can't just switch one day and start using that feature of Python 3. And because it's one big language that you have to start using all at once, you've got to sort of swallow the things that are difficult to swallow along with savoring the things that you actually want. So to bring this back to what we care about, how can ECMAScript 6, which is the technical standards name for the next version of JavaScript, avoid this trap, the Python 3 trap, if you will? So my crazy idea, which I'm giving myself too much credit to call my idea, but it's something I've become passionate about in the last year or so, is that we might be able to ease ourselves into the new version of the language by simulating its most useful features in the current version of the language, right? So why would we want to do that? Obviously, there's a cost to simulating features, and if you could just switch to the next version of the language, you'd get native support for all those things, and wouldn't you be better off? Well, I think the insight here is that at every step of this process, you have this perfect hybrid of the old language and the new that suits your needs exactly. And you know exactly why you've adopted each of its features. You get to prove them out even before they're fully standardized. And you know that the language you're using is the language you want to be using, and there aren't these hidden dragons that you're going to have to confront at some point. So a phrase that I might have come up with for this is linguistic time travel. We're reaching into the future and selectively taking parts of the future of JavaScript, bringing them into JavaScript of today. So what's an example? Well, this is not generator related. This is a sort of simpler but also cool feature of ECMAScript 6. Arrow functions are a nice way of writing the hundreds of little throwaway callback functions that you need to write in JavaScript. So you get to do away with the function keyword, and you can just have an expression instead of a whole curly brace delimited body with a return statement in it. So these two things are equivalent if you're running ES6. But there's a fairly straightforward translation from the futuristic syntax to the syntax of today. And if you find these slides online, you'll see that this is all sort of live editable in case you want to play with it and see how it works. And now I've ruined it. Oh well. OK, so how does that work? Well, we've got a tool chain that we use at Facebook that I've worked on, and that is open source. It actually predates my time at Facebook. I started working on it when I worked at Quora. It's called Recast. And it has some utilities for traversing what are called abstract syntax trees, which are these sort of object graph representations of your code, and ways of telling what type of node you're looking at, and also ways of building up new kinds of nodes. So you call recast.parse with a string of code that gives you back this tree, and then you need to modify the tree. Hope you can see this. The slides are at benjaminwithoutthei.github.io/JSConf2014 if you want to pull that up. Okay, so we're traversing the tree starting at the root of it, which is typically like the program type node. And this callback function is going to be called on every node. And we just want to only do anything for the arrow function expression nodes, because we're going to try to get rid of those and turn them into plain old, good old-fashioned functions. So we grab the body of the arrow function expression, if we find one. And if it's an expression function, that is, it doesn't have a curly brace block statement body with a return statement in it, we want to turn it into one of those, because expression functions are not legal until we have ECMAScript 6. So I guess that's another feature that we're supporting here. Oops. And then we want to create a new function expression using all the same properties as the arrow function expression. Basically, the only thing that's different is the type is function expression now instead of arrow function expression. And then one of the conveniences of arrow functions is that they automatically bind to the value of this in the enclosing environment. So we have to simulate that as well. So we're going to make a member expression out of our function expression and the identifier bind and call that as a method passing this to it, right? And then all that remains is to replace the original arrow function expression with this bound expression. And then you call recast.print with that same abstract syntax tree, grab the little code property off of the object that it returns, and print that however you want, or write it to a file. And it prints out the thing that we were trying to create. Cool. So that's sort of a warm-up example of transforming code at the abstract syntax tree level. And if you already have a build step for static resources, you can have this newfound ability in a matter of minutes if you use Browserify or some other static build pipeline. So what is this recast thing? Well, I came up with the name when I first wrote it. I thought it was clever because it recursively traverses abstract syntax trees. So rec-ast sort of makes sense at that level. But it's also a word, an English verb, which means to like melt some metal down and reshape it, or arrange something again, remodel, supply a theater work with a new cast, that sort of thing. So I also like to think it has some poetry to it. So how do you use recast? Just to recap, you require it. You call recast.parse on the source, and then you get to do literally anything you want with the abstract syntax tree. Recast doesn't care. It does bundle a suggested traversal tool, but you really don't even have to use that, and I'm not even super thrilled with it, so I'd recommend you find anything that works. And then you call recast.print with the modified abstract syntax tree and do whatever you want with the resulting string. So that's how it goes. And what's magical about this? Like, you could just pretty print the result, and that would give you working code. You'd be able to use ECMAScript 6 today, which is part of the promise here. But there's another property of recast that's pretty cool that's, I think, best described as non-destructive partial source transformation. So it will try to reuse original source code for parts of the tree that you didn't modify, which is cool, both because it lets you write transforms and then generate human-readable diffs, and I've done this to great success in my job at Facebook, and because since the printer knows where those original fragments of source code are coming from, it can actually give you really good source maps for free, totally automatically, for any arbitrary abstract syntax tree transform you might want to write. So if you like source maps, that might be pretty appealing. So this presents a moral hazard of sorts. You can start writing scripts that rearrange the furniture in your code base ad nauseum and appear to be the most productive programmer anyone has ever seen and the laziest at the same time. Or you can, in the Gandhian sense, be the change you want to see in the world. And my confession is that I gave in to that temptation, the first temptation, for a time. There was a couple of weeks or months at work where I had written a script that would translate a lot of old idioms for defining classes in JavaScript in our code base to the new ECMAScript 6 class syntax. And I was just running it over tens of thousands of files coming in the morning and spending 5 minutes or so doing that and then waiting for humans to review those diffs. And it's remarkable both that they were able to review them and that in a lot of cases they didn't realize that this had actually been generated by a script. That's the beauty of recast. And all told, I only converted 1,600 or so files for like a combined 150,000 insertions and deletions worth of diff. And I guess you can tell from this, we have about 1 class per file, so 1,658 classes. The cool thing is that we now have 3,500, almost 3,600 classes in the code base today. And you know that those extra classes got written by people who just looked around at the code base that had been sort of bootstrapped into the new style, and they did what they found everywhere else. They mimicked the style, as you should do in any large code base. So that's the real value of this kind of automatic source transformation. If you get nothing else out of this talk, there's a cool Unix tool called Parallel that lets you write really simple, single-threaded scripts that take one argument and then run a whole bunch of copies of them appropriate for the number of cores. I have 32 cores in my dev machine at Facebook. So I was able to do something like 230 sort of subjective seconds worth of work in 12 seconds. So that's cool. I gave a whole talk, actually, about this project a couple of months ago. So these links will take you there. OK, so what about something a little trickier? As promised, we are going to talk about generator functions. So here's an example of a generator function. And I apologize that it's not like Fibonacci or something like that. It's a little bit more sophisticated. This had all of the things that I wanted to talk about in it. So that's why I chose this function for printing out or rather yielding each of the permutations of a given list. So I had to look this up to remind myself how to do this. So the way it works is if the list is just 1 or 0 elements, that's the only permutation of the list. So you yield that. Otherwise, you take the list consisting of just the first element in the list, and then you take all the permutations of the rest of the list. And for each of those child permutations, you sort of walk the first element through it at each place. So none of those permutations contain that element, but then you put it back in at each possible place. And so when you yield each of those things, you're yielding all of the possible permutations of the list. And here's an example of how you might use it with the list 132. I'm going to get some water. Actually. So if you're used to generator functions in Python, you may not be used to the next method of the generator object, returning a little object that has a value field and a done field, but that's the API that we've decided on for ECMAScript 6. So in each of those cases, the value is one of the permutations, and done would be false, but then at the very end, done is true, and the value is undefined. So that's what that's about. There's also another syntax a prettier syntax for iterating over the values of a generator, the for of loop. So it's easy to confuse this with for in, but it iterates over the values of its argument instead of the keys. So how hard could it be to translate this futuristic syntax into something that runs in a browser today? Well, this was like May of 2013. I thought it was funny to tweet cryptically about having almost finished my life's work, and boy, was that hubris, because I wasn't anywhere close to being done. The project was actually called Degenerate at that point, which is sort of self-deprecating is my style, I guess. And I was so far away from being anywhere on top of this project that I'm glad I didn't actually identify in this tweet what I was talking about. It's basically the trickiest code I've ever written, which may say more about me than the code itself. But I also think it's about as tricky as transpilation or source transformation gets. So if you absorb any of this, then that's great. You've absorbed something that is probably the best example of a really nasty source-to-source transformation, and you can do anything at that point. OK, so here's our original function. And what's the first step? Well, it's going to turn out to be convenient if we take all of the variable declarations from inside of this function and hoist them to the top of the function, which is something that JavaScript does anyway. So first PS, P, and I are now declared at the first line of the function, and wherever they used to be variable declarations, those are just assignment statements, right? So why do we do that? Why does that matter? That doesn't actually change anything yet. Well, I'm going to introduce a couple more variables, some temporary variables, and a loop variable. Yeah, OK. And the reason for that T0 and T1 is that we're going to turn the for of loop just into a while loop so that we can treat it the same way as any other while loop. So if you see for P of PS, it's now going to change into this call to the values function of our little runtime object wrap generator. And then it's just going to iterate over that generator calling next until it's done. And each time it will assign the value to the loop variable P. So now we've got a plain old while loop. Don't have to care about for of loops anymore. OK. So still haven't really changed anything. Still have yield expressions, and it's still a generator. But now we're going to return an anonymous generator that doesn't take any arguments. It's just a closure that has all of those variables in its scope. And so now we're beginning to get somewhere. And so this is a big leap, but we need to turn the body of this function into something that can execute in JavaScript of today. And my idea for how to do that was to have a switch statement inside of a while true loop, where the cases of the switch statement are jump targets that we can sort of jump to as if we had a go-to statement in JavaScript, which sounds like the worst thing in the world, but ends up being pretty cool. So the first one is case 0, as you might imagine. And this is going to test to see what the length of the list is. If it's less than 2, we're going to jump to case 5. And we do that by setting context.next to 5 and then breaking, which you'll note breaks out of the switch statement, but not the while loop. So we loop back around for another iteration. Context.next is 5. And then, well, case 5 will come later. You may remember in this case that we wanted to yield the list itself. So the way we do that is by returning the list. So that's the answer to what happens to the yield expression. It becomes a return statement. But we want to know where to come back to after we call back into the generator next function. So we set context.next to 3 in this case, which is the next case. And if you remember in that case, after we yield that one value of the list, we're done. So we're going to jump all the way to the end, which happens to be case 19, which you can see over there on the side. It just calls context.stop, which shuts everything down and frees some memory. And so that's the abort, abort case. But in case the length was not less than 2, then we were going to jump to the 5th case. And here it is. This is where we call, where we get the first element as a list, and then the rest of the permutations and the values of that permutations object. And we deliberately fall through, which is another thing you should probably never do when you're writing a real switch statement. But in this case, it is intentional that we fall through to case 8. Case 8 exists just so that we can jump back to it, by the way. And then if we are done with the generator, we're going to jump to case 19, which is the final case. Otherwise, we're going to set the loop variable to the value of the most recent thing that was returned by the generator next method. And now here's our sort of obliterated, eviscerated for loop. We're setting I, the loop index variable, to 0, and the loop head location is this case 11. And while I is less than list of length, we're going to jump to 17. Or in case it is not less than length, we jump to 17. Otherwise, we plan on jumping back to 14 after we yield this expression. And I think this is a good illustration of what's cool about recast. So these comments here, this practice that people have, some people of lining their comments up vertically, especially when all the words are the same length, and it's just so visually pleasing. That's very idiomatic. It's very hard to capture in code to identify the intent of that formatting and try to recreate it later if you're pretty printing. So the fact that recast is able to just take that whole array.prototype.concat.call blah expression and just copy it over to the output, and you'll notice it's actually indented it by 2 spaces, means that in large part, the parts of the tree that you haven't touched just carry over all of their idiomatic formatting, and you don't have to apologize for that when you submit a diff for humans to review. Okay, so we're yielding that permutation, which is the concatenation of a prefix and the first element and a suffix. And then coming back to case 14 the next time we call into the generator. And this is the update case of that for loop. So we're incrementing the loop variable and then jumping back to case 11, which was the head of that loop, where we test the length. And eventually, I is not going to be less than the length anymore. And so we're going to jump to the case 17 here. And where is that taking us? Let's see. Oh, remember, we were inside of a while loop, so we need to jump back to the head of that while loop and then continue testing the result of the generator to see if we're done finally. There are a lot of permutations of even small lists, so you can see how this ends up generating a lot of them. But that's it. That's JavaScript that runs in a browser today. With one exception, I still haven't explained where this context object comes from, and I'm going to sort of wave my hands here, but we're going to pass the whole anonymous function to this wrap generator runtime function, and that'll return the generator object that has the next method, and also make sure that the context gets passed in each case. Okay, so if you stuck with me through that, then you understand how Regenerator works. Yeah, well, that's a good question. Yeah. Yeah, if I could make it prettier, I certainly would. But I will say this is a function that has like multiple yields in it and loops and everything, so it's like a good example in a fairly compact space of like all the features of Regenerator, which is contributing in part to it looking pretty messy. But you could imagine stepping through this and debugging the code with a little bit of context, I hope. Maybe that's wishful thinking. All right. So that's all well and good. You can convince yourself, if you stare at that code long enough, that it kind of does what it's supposed to do, generate some permutations. But how in the world do you programmatically generate code like that from ECMAScript 6? So I'll show you how a for statement, which is the normal like 3-part for statement rather than a for in or for of statement, gets code generated. All right, so this is an actual case from the emitter code for Regenerator. So when we encounter something of type for statement, we first create a series of locations. And these are sort of like uninitialized literal numeric values that are going to end up becoming jump targets and case labels in that switch statement. And so if the for statement does have an init part, the like variable declaration thing, we're going to explode that, which is my sort of made up terminology for turning it into like a state machine if it contains any yields. And then we're going to mark the head to say, now we're at a place where we would want to jump back to if we were doing another iteration of the loop. If there's a test in the for statement, and there doesn't have to be a test, then if the test is false, we jump to the after location. And note that we don't even really know where the after location is yet, but it's still fine to plan on jumping there when we do know. And then because this is a loop, we want to keep track of what loops we're inside in case we come across a break or a continue or a return that we need to interpret in that context. So there's this leap manager. Leap is my made-up term for a break or a continue or a yield or a throw that knows how to deal with those things. And we're putting a new loop entry onto that stack and then exploding the body of the loop. And now, after the body, we are going to emit the code for the update part of the for statement. And so we need to mark that so we can jump to it. If there is an update part, I guess I might have been able to avoid marking it if there wasn't, but I did. Then we generate code for that, and we emit some code that jumps back to the head of the loop. So we're going to go right back to the test part, and then mark the after part. And so now we've marked all of our locations. They have actual numeric values and can be used in the code that's generated. And now we're done. So we break out of this case. We've successfully emitted code for a for statement. So how does loc work? It's actually dead simple, simplest thing in the talk. It returns a literal abstract syntax tree node object, initialized to -1, just as a sentinel for this is not good yet. And then when we mark it, we're keeping this listing of all of the statements that we've emitted so far, so we know what the next one, what the location of the next one is going to be. So mark assigns that location to whatever literal node you pass into it, and goes ahead and initializes it and has some assertions about it not being already initialized and so forth. So once we've marked something, we know that we're going to emit a case statement in the switch statement eventually. All right, so b.literal and n.literal may be a little confusing. Those are actually provided by recast. If you recall, you could say require recast.types.builders.literal and require recast.types.namedtypes. Cool. All right, so this is an example about how that jump if not thing works. And it's pretty straightforward, but I'm not going to spend time on it right now. Basically, you do some assertions, and you try to avoid having double negation if possible, just because that was a problem that I could fix, and it makes the code nicer. And then you emit an if statement that sets the context.next property to the next location that you want to jump to, and also emit a break statement. So I know I raced through that, but I think it will be self-explanatory if you were to go back and look at it. All right, so explode statement is the last of the sort of drill down examples that I want to talk about. And I don't think I actually have time to go through it, but the interesting part about it is that Regenerator understands whether a statement or an expression contains any yield expressions or any problematic breaks or continues. And if it doesn't, in my terminology, contain a leap, then we can just emit the statement as it was. So a large part of the performance promises of Regenerator are that if you're not using yield in a certain part of your code, it just is left untouched. You could imagine, exploding everything out into a big state machine that is much longer than your original code, and that would be, perhaps logically correct, but not performant or very easily compressible. Okay, another exciting part is what happens if an exception gets thrown in the middle of the state machine, and the secret to that is remembering where you last knew that you were and having a little map that can be inspected to figure out what try statement or catch block or finally block you're inside of, and it sort of twiddles context.next and then calls back into the generator, and so you appear to resume at the place where you expected to. For instance, if an exception is thrown by this block, you'll resume in the code that was emitted for the catch block. So this whole example actually works and ends up being surprisingly short. And I'll leave that for you to go through if you are so inclined. And then here's the runtime code that supports all of that. And the interesting thing about this is that it's invoking this in the very middle, the inner function. That's the function with the switch statement inside of it that we've been talking about so far. And so that's where you see it's passed in the context, and we get the value back out. If everything is OK, we return the object with value and done properties. If there's an exception, then we call context.dispatchException with that exception value, and that's what sets everything up for control to resume in the exceptional control path. All right, so the good news is, as mentioned earlier, this is pretty much as hard as it gets, which may not sound like good news, but this was a hard project for me, I'll be honest. And it took a while to wrap my head around these things. And so it means nothing if it takes you a while to wrap your head around them as well. But if you've picked up on anything here, at least gotten a sense for how complicated this is, or in the end, how tractable it is, then that's great. And you can do a lot of smaller things, like adding support for async functions and await expressions to the language in like this much code. This is the entire runtime for that really cool ECMAScript 7 feature that's coming down the pipe, and that's already implemented in a pull request for Regenerator. But I just mentioned that's an ECMAScript 7 feature, not ECMAScript 6. So we're not just bridging the gap here between today and whenever ECMAScript 6 is fully supported. We're always going to be looking into the future. So my motto is always be transpiling, because incremental transpilation is the key to avoiding that Python 3 trap for JavaScript. It's how we bring about the future without choking on it. And it's how we know that the future is actually going to be pretty great, because it's, as I said before, linguistic time travel of a sort. Still really hard. Not everything can be transpiled. I don't know what to do with ECMAScript symbols. And AST transforms don't always play well together. Two transforms could be competing to be like the thing that adds something to the first line of a function. And who wins? Well, you have to figure out which one should come first. You have to break that tie, and you can't really do that automatically. You really need to have something like source maps when you're debugging generated code like we just went through, because it's not as readable as the futuristic syntax for sure. And the language specification can totally change out from under you. Async and await, not specified yet. Might have to rewrite that pull request, but it wasn't too much effort in the first place, so I'm going to try to track those changes as they come. So my team at Facebook, JavaScript Infrastructure, is going to be working on this as long as it takes to make the process seamless. And it's all going to be open source. We're just getting started, and you are absolutely more than welcome to help. Thanks very much.